Let's go ahead and look at the first and easiest one, and that's the element effect, okay? So the element effect determines how loosely or strongly a particular element bonds with hydrogen. Okay? And we can use these effects to compare different protonated elements to each other. So for example, a perfect example of using the element effect would be having like a nitrogen attached to an H and a sulfur attached to the H. Do we know the pKa of the nitrogen? Actually, yeah, I taught you guys that the pKa of NH3 should be around 38, right? What about SH2? Did I teach you that one? I actually didn't teach you. So then in this case, if I were to ask you guys which one's the strongest acid, you would have really no clue on how to tell me because I never gave you the pKa of SH2. So that's why we have to use these factors, okay? So it turns out that the element effect is going to consist of two trends, and the first one is electronegativity, okay? So electronegativity just says that the stronger the electronegativity, the more willing the molecule will be to accept a lone pair as the conjugate, okay? So here's the electronegativity trend. I'm just going to say En. And what that basically says, let's just put it this way. We have, let's say, HF, okay, which is an H attached to the most electronegative atom. And then let me say that we have also CH with also then H3 over here. Okay, so I'm just giving you, then that's a little bit off the screen, but can you see that that's just an H on the side? Cool, like right there. Okay, so anyway, we've got HF and we've got CH4, all right? And what I'm wondering is, after each of these molecules gives up a proton, what is it going to look like? Well, after this gives up one proton, H+, what it's going to look like is this, F-. Does that make sense? Because you always exchange a proton for a lone pair. So it's going to turn into F-. This is the conjugate base. Okay? Now let's look at the conjugate base for the carbon. The carbon, when it gives up its proton, by the way, I'm drawing this arrow wrong. This is not a mechanism arrow. This is just like me showing what happens next, okay? What that would look like is like this, CH3-. Okay? So these are my two conjugate bases. My question to you is, which of these conjugate bases is the most stable? Which of these is the happiest having that lone pair or that negative charge on it? And obviously the answer must be that it would be the fluorine. Why? Because fluorine is the most electronegative, so it's the one that's happiest having electrons on it. Whereas carbon is really not electronegative, so carbon sucks. This carbon is really, really bad. That's like a terrible happy face, sad face. This carbon is really, really bad. This fluorine is like kind of happy. It's okay because it's very electronegative, so it doesn't mind having the lone pair. So does that first trend make sense so far? Now let's look at our periodic table here. We were comparing nitrogen and sulfur. Okay? So nitrogen at the periodic table is here. Sulfur is here. So just with the electronegativity trend, which of these do you think is going to be the better acid? The nitrogen or the sulfur? Hopefully you said the sulfur, because even though you don't know the pKa of the sulfur, you know that the sulfur is more electronegative. Is that cool so far? So it's going to be happier with the negative charge. But now it turns out that there's another effect that we need to know, or another trend that has to do with the element effect. And that one is the size trend. Okay? And what the size trend says is that the bigger or the squishier that the atom is, okay? I'll explain what squishy means in a second. The more willing it's going to be to accept a lone pair. So I'm going to give you guys now two more examples, still using fluorine. So imagine that I have F-, and F- looks like this, okay? The negative charge has to do with like a lone pair that accepted over here, okay? Now, what I just drew was the electron cloud. Like there's a lot of electrons circulating, and I just drew like the electron cloud. Now let's compare that to iodine. Iodine is at the bottom down here. Iodine is a much bigger atom, okay? I mean, the atomic number is like, I think that's 53. So it's really, really big. It has 53 electrons. So instead, iodine is going to look like a sun compared to fluorine. It's going to look massive, okay? So iodine's super, super massive. Fluorine is little. And iodine also has a negative charge, okay? And it also has a lone pair, okay? So which of these do you think is going to which of these do you think is going to be most affected by the lone pair? Okay? the answer is that fluorine is more electronegative than iodine, okay? I agree with that. But also, fluorine is a lot smaller, so that means that it's going to feel the effect of that negative charge way more than the iodine will. The iodine is so big, it's like, I don't care. Like, I don't mind having an extra lone pair because I'm massive, okay? And that's what I mean by squishy. It's like really like big and squishy. It has a ton of electrons everywhere. Whereas fluorine is kind of small. Even though it's very electronegative, it still is way smaller. So overall, it's going to experience the effects of that negative charge more than the iodine would. All right? The iodine honestly doesn't care. It could give up an electron. It could gain an extra electron. It doesn't matter. All right? So the answer is that with size, you also become more acidic. The further down you go, the more acidic you are. So if I were to compare HF versus HI, okay, and I went ahead and I gave up a proton in each of these, what I would become is F negative, and I would become I negative as my conjugate bases. And then which one would be the most stable conjugate base? The I negative. Why? Because the I negative, like I drew, is much, much bigger, so it's going to be able to distribute those electrons in a much bigger space than the fluorine will. So it's going to be more stable, okay? So that means that the stronger acid is going to be HI, okay? Cool. So hopefully that makes sense to you guys in terms of the element effect. Now just keep in mind that the element effect only has to do with atoms that are hydrogens that are directly attached to different atoms, okay? So let's go ahead and do these examples down here. So for one, I'm going to have you guys, we already did some of these, so I was just kind of working ahead, but showing you guys using the element effect. So for one, go ahead and take a break and try to solve this one and predict which one is going to be more acidic, all right?